So today we're going to be talking about inverse relations. And with an inverse relation, we're just talking about a function and then its inverse. And so we're going to look at this numerically, algebraically, and graphically. And so we start out with a set of data here where our x value and our y values are shown in a table. And to find our inverse numerically, because when talking numerically, we're actually referring back to a table. And the only thing that we need to do to look at this numerically is to take all of our x's and replace those in our y's. And all of our y's then become our x's. So basically, we are doing nothing more than just flip-flopping our x's and y's. And so when before we begin, we first want to make sure that this set of data, and we call this a relation before we realize whether or not it's an actual function, we look at our x values, and I do not see anything that is actually repeating, which makes that a very easy set of data to reference, saying that it is a function, because I do not have any x's here that are repeating. Had there been a repeating x, which is perfectly fine, so let's say that we have a -2 that's repeating. In order for this to be a function with a repeating x, the y also needs to be exactly the same. It also needs to be a unique y. So for that x, you have to have a unique y. And so understanding that, we can say that the original relation of this is a function. Yes, because x has a unique y. So for every x, there is a unique y. I don't have an x and then it has two different y's that go with it. So it is a function. So then to take this as a inverse, I'm going to take the x's and replace those x's in the y column over here on the right-hand side. And I will do the same thing with the y's. The y's then become my x's. That's how I can find an inverse with numerically. So then I'm going to ask the same question. Is this inverse, is this a function? I look at my x's. I have a 4, a 5, a 3, a 4. So here I have a repeat. I notice the x up here has a y value of -2. The x down here of 4 has a y value of 1. So therefore I can conclude that no, this is not a function, because the x's that I have resulted in two different y's, and we cannot have that as a function. And the same thing goes with my 5's. I ended up with two different y's as well. So not only do my 4's make it not a function, but my y's, or excuse me, my 5's as well. Numerically, looking at that as a function or not. The horizontal line test determines whether or not the inverse of a function is a function. A lot of function words going on here. So what you have is, if you have a graph, and I'm going to use, I'll just make up a graph here. Okay, kind of got an opposite of a cubic going here, inverse of a cubic. And I perform the vertical line test on this graph, and sure enough, it passes the vertical line test so that I can say that this graph is a function. But to determine whether or not the inverse of this graph is a function, I would perform what's called a horizontal line test. And if it passes the horizontal line test, then the inverse is also a function. And the same goes true with the horizontal. If it only crosses the graph in one spot, then yes, I could say it passes the vertical line, or excuse me, the horizontal line test, which means that the inverse of this function would also be a function. So we look at these graphs here, and you could put these into your graphing calculator, and we see that this first function is the reciprocal function. And so I'll just do a real quick little sketch here of a reciprocal function. And so I know that it already is a function, but to determine whether or not the inverse of the reciprocal is a function, I would perform the horizontal line test. And knowing that this is an asymptote on the x-axis, as is the y-axis being an asymptote, I can say yes, this does pass the horizontal line test as well, so therefore the inverse of this reciprocal function would be a function. We have a linear graph here, And the linear graph would be looking something like that, and actually it would be crossing up, it'd be up higher, but it too would cross the, or pass the horizontal line test. So yes, this is, the negative 3x plus 7 is a function, but its inverse also would be a function. I look at my parabola, parent function. This is a function, but I look at the horizontal line test and it does not pass as it crosses in more than one spot. So the inverse of the squaring function would not be a function. And then I have my cubic that looks something like that, and it too would pass. And so therefore the inverse of a cubic function would also be a function. So that would be graphically looking to see whether or not we have functions of the inverse. A one-to-one function is classified as a function that obviously is a function, but its inverse is also a function. So looking up above, our reciprocal function is one-to-one. Our linear is one-to-one, or identity you could say. And cubic, the cubing function, is also a one-to-one function because these three are functions, but yet their inverses are also functions. So graphically. Then we want to find an inverse algebraically. And as we saw with the table, we flip-flop the x's and y's. And here we're going to do the exact same thing. Understanding that f of x is the same thing as y, I will just replace f of x with y. And it makes it clearer now how I can take each variable then and replace it with its appropriate opposite. So the y becomes an x and this x becomes a y. And then all the way through this, I'm going to just keep in mind that I am solving for y. So my first step is I add 6 to both sides, and then I will be dividing everything through by 3. So I get x over 3 plus 6 divided by 3, which is 2, is equal to y. Now, I want to make sure that I am representing that I have found my inverse, so I will use the notation for an inverse function as f raised to the negative 1, understanding that that does not mean a negative exponent, that is just this notation for inverse, equals 1/3 x plus 2, making sure that I have that in proper form, pulling the 1/3 out of that variable. And then there is my inverse function. Looks like it's a linear function. Doing the same thing with a square root, I understand that f of x is y, so I'm going to replace that with y equals the square root of x minus 3, flip-flop my x's and y's. To get rid of a radical, I will square both sides, because to undo a radical, I can square, so I end up with x squared equals y minus 3. Adding 3 to both sides gets my y by itself, so I end up with y plus 3, that would be x squared plus 3 equals y. Writing that in proper inverse notation, f to the negative 1 of x equals x squared plus 3 would be my final answer. Flipping to the back side of our notes, we have a little bit more complicated problem, not one that we can't handle. And again, we're going to work this the same way as we did the others, replacing f of x, knowing that that is the same notation as y, is equal to 2x over x minus 1. Flip-flopping my x's and y's, I get 2y over y minus 1. Our problem that we see here is that we have a variable on the numerator along with a variable on the denominator. So we're going to start by getting rid of the denominator first. So I'll multiply both sides by y minus 1 to get the y minus 1 out of the denominator there. So I get x times y minus 1 equals 2y. Just makes things a little bit neater and nicer to work with. Then I will distribute that x to everything inside that parenthesis. So I get xy minus x equals 2y. Now, keeping in mind Our goal is to solve for y. And that's going to be hard to do when I have a y on the left and a y on the right. So I'm going to combine my y's onto the same side of the equation. I will do that by subtracting xy from both sides. Now I see that I have y on the right, or both y's are here on the right-hand side. Now, my goal is to solve for y, so therefore I need to pull the y out of each one of those terms. I end up with, and I will be factoring that y out. It's kind of like I've got a common factor there. And by factoring a y out, I end up with 2 minus x. Now, my goal, remember, is to solve for y. I want y by itself. I can get y by itself if I divide it by that factor that it's being multiplied by. So I will divide both sides by 2 minus x. So I get the opposite of x over 2 minus x is equal to y. And there I have it. My y is by itself. Writing it in inverse notation and factoring a -1 out of the numerator and factoring a -1 out of the denominator, I end up with x over x minus 2. And that is my final answer. The inverse reflection principle just says that when we're looking at an inverse, we're reflecting it over the axis, and this might have you finding by sketching it out. We are not going to do that by hand, but what we can do is practice all of the numeric, algebraic, and graphic properties that we have learned so far. So first thing we'll do is we will do it numerically. If I make my own set of x and y values, if I plug -2 into the x here, -2 cubed is -8. -8 plus 1 results in -7. Let's go to -1. -1 cubed is -1 plus 1 is 0. If I plug 0 in, 0 plus 1 is 1. 1 cubed is 1. 1 plus 1 is 2. 2 cubed is 8. 8 plus 1 is 9. And then the inverse of that, I just flip-flop my x's and y's, and I look at, now this becomes -7, 0, 1, 2, 9, and my y values for that become -2, 1, 0, 1, and 2. I don't have any repeats, so it looks like that this inverse also would be a function. Then to change this algebraically into the inverse, I would say y equals x cubed plus 1, x equals y cubed plus 1, subtract 1 from both sides, x minus 1 equals y cubed. I don't want y cubed, I want y. So to undo, I will take the cube root of both sides. That undoes that, and I'm left with the cube root of x minus 1 is equal to y. Writing that in function notation, I get inverse of x minus 1. The cube root of x minus 1. Now, we go to verifying inverse, and we can do that using the composition rule, meaning composition of two functions, f of g of x and then g of f of x. If we get it out to our single x, therefore we can then determine that the function that would be created from the composition would also be a function, the inverse of that. So it'd be, is f of x and g of x, are they inverses of one another? So if I would give you a couple different functions and say, are they inverses of each other, you would use composition. So I will take f of g of x. So to find f of g of x is going to go inside of f of x. So that's, I would have the cube root of x minus 2. That would be quantity cubed because g is going inside of x plus 2. I know that the cube root and cubing undoes each other, and so I'm left with x minus 2 plus 2. The 2's cancel, and I'm left with my identity of x. And then I'll do the same with g of f of x. It needs to work both ways to verify. So now f of x is going to go inside of g of x. So instead of x, I'm going to put x cubed plus 2 and then minus 2. The 2's cancel. I'm left with the cube root of x cubed. We've already talked about that those cancel each other out, and I'm left with my identity of x. So therefore I can say that f of x and g of x are inverses of each other because through the composition it came down to the identity of both of those, and therefore they are inverses.